This lecture is part of an online course on algebraic topology and will be about calculating the fundamental group pi1 of a space X. So we remember from last lecture that pi1 is the set of homotopy classes of maps from S1 to X, although strictly speaking I ought to choose base points in X and S1. And we saw that the fundamental group of a circle with respect to some base point is just isomorphic to the integers. And what I want to do this lecture is to give some slightly more complicated examples. First of all, it's easy to calculate the fundamental group of a product of two spaces with respect to a base point. This is just the product of the fundamental groups of the two spaces. And I'll miss out the base points because I'm getting bored of writing them in. And this is very easy because the maps from a circle to X times Y just correspond to pairs of maps from a circle to X and a circle to Y, and from that it's quite easy to check that the two fundamental groups are the fundamental group is just given by product. An example of this is the fundamental group of a torus. So we might have a torus in R3 looking something like this. And that's easy because the torus is just isomorphic to S1 cross S1. So the fundamental group of the torus is just pi1 of S1 times pi1 of S1, which is just Z times Z. And it's fairly easy to see what the two copies of Z are. One copy of Z is you go round that way, and the other copy of Z kind of corresponds to going round this way. Next, we can try asking what the fundamental group of a union of two spaces X and Y is. Well, if you've got a disjoint union of X and Y, this is not terribly interesting because if we choose a base point in X, we're just going to get the fundamental group of X and so on. So we can get a rather more interesting example if we take the fundamental group of X and Y, except we join them at the base point. So here's the base point of X and the base point of Y, and we've taken the disjoint union of X and Y and then identified the base points. And we can ask, what is the fundamental group of this? This is sometimes called the wedge sum of X and Y, and denoted by X. Not wedge, whatever this V sign is. So we ask what X, what the pi1 of X and Y joined at a point is, and there's an obvious guess for this because there's a map from pi1 of X to this space here, and there's also a map from pi1 of Y to this space here, both of which are pretty obvious. And if you've got two groups, there's something called the amalgamated product of these two groups, or free product of these two groups, where you just take the universal group generated by these two groups. So there's a natural map from this free product to the fundamental group, and the obvious question to ask is this an isomorphism? And it really ought to be an isomorphism. Unfortunately, it sometimes isn't. And there's a sort of weird counterexample to this given as follows. First of all, we can take the following space. What we do is we take a union of a whole lot of decreasing circles. So it's, you can think of it as being a sort of earring. It's sometimes called a Hawaiian earring. So there's an infinite sequence of circles all getting smaller and smaller, all passing through this point here. And if you ask what its fundamental group is, the fundamental group of this is really rather hairy because you can go round this circle, then round the next smallest, and then round the next smallest. So you can have a loop that goes round all these infinite numbers of circles, and after it's done that it could go back around this loop again. So the fundamental group is really very complicated, and I don't really want to know what its fundamental group is. So what I'm going to do is I'm going to kill off the fundamental group as follows. What we do is we just take this Hawaiian earring and we form a cone over it like this. So we choose a new point here and just form a cone over it like that. And now the fundamental group of this is just trivial because this space is actually contractible. You can just squish it all down onto this point. And we can take another copy of this weird cone over the earring. So I'm going to take a second copy and I'm going to join them together at this point here. So we've got two copies of these cones over this funny earring. And of course the fundamental group of the second copy of this cone is also trivial. So you might guess the fundamental group of the whole thing is going to be trivial, but it's not quite, because I can take the following funny loop. I first go around this big circle, and then around this big circle, and then around the next biggest circle, and then around the next biggest circle, and I sort of keep on going like that. And the trouble is, in order to undo all these loops on the left, I need to push everything down to the vertex of the cone on the left. In order to undo all the loops on the right, I've got to push them down to the vertex of the cone on the right. But the trouble is they're so tangled up with each other that you can't sort of simultaneously push everything down to the cone on the left and down to the cone on the right. So the fundamental group of this is something horribly complicated that I don't even want to think about. And the problem here is that this cone over this earring has this rather weird point here where an infinite amount of stuff is happening. And roughly speaking, we find that the fundamental group of a union of two things joined at a point is what it ought to be, provided things aren't too messy near the point you join them at. In fact, there's a variation of this. Suppose you've got two sets x and y. And maybe, suppose you've got a space that's a union of x and y, and their intersection is some sort of non-trivial space x intersect y. And you want to know what is the fundamental group of the union of x and y. And there's an obvious guess. We might take the fundamental group of x and take the free product with the fundamental group of y, and then quotient out by the things that are in the union, in the intersection of x and y. So this is a sort of free product with amalgamation. You take the free product of pi1 of x and pi1 of y, and you kind of identify the subgroup they have in common, which ought to be pi1 of x intersection y. So we certainly get a natural map from this space to the union of x and y. And we can ask, is this an isomorphism? Well, of course, it's not in general. There are some conditions we should have. First of all, we want x should be connected and y should be connected. And then you stop and think about this a bit and you remember these should actually be path connected because we're working with paths rather than ordinary connectedness. And you also want the intersection x and y to be path connected. If the intersection of x and y isn't path connected, then you see you can get things like this. X might be a sort of semicircle and y might be the other half of a circle, and then x and y both have trivial fundamental group, but the fundamental group of their union isn't trivial, and that's something to do with the fact the intersection is not path connected. Well, this isn't enough because we have this sort of weird counterexample with cones on earrings and so on. So we need some extra condition. And one extra condition you can add is you just say x and y are open in the union x union y. This condition is actually a bit of a nuisance because in examples when you want to apply this, it usually turns out that x and y are closed subsets rather than open subsets, but that turns out not to matter so much, because if you've got an open subset you can usually do a deformation retract to a closed subset, and that's more or less good enough. Let's just sketch roughly why Van Kampen's theorem is true. I'm only sort of going to prove about half of this. So we want to show that pi1 of x, taking the free product with pi1 of y over pi1 of x intersection y to pi1 of x union y is an isomorphism. So we need to show two things. We need to show it's onto, and we need to show it's injective. And showing it's injective is kind of a little bit tricky, and I'm going to skip that bit. Showing it's onto is rather easier, because what you do is you notice that x and y are both open. So if you've got a map from S1 to x union y, it means every point of S1 has a neighbourhood whose image lies either in x or in y, because x and y are open. So we can find a finite number of points of S1, say S1 up to Sn, such that S1 is covered by neighbourhoods of these points, and each neighbourhood is either in x or y, and that follows because S1 is compact. So we're using the fact that S1 is compact and x and y are open. So what our path is doing is it's starting here, and then it wiggles around in here for a bit, and so this would be the image of a neighbourhood of S1, and then it wiggles around in here for a bit, and that would be a neighbourhood of S2, and then it might wiggle around in x for a bit more, and that would be a neighbourhood of S3, and so on. So any path in here can then be represented as a product of a finite number of paths that are either all in x or all in y, and that's enough to show this map is onto. Showing it's into is a little bit trickier. You need to, instead of taking S1, you need to take S1 times the unit interval and cover it with a finite number of open intervals, each of whose image lies in x and y, and then think rather hard about it. Anyway, let's give some examples of this. So first of all, let's take two circles joined at a point. And now I want to apply Van Kampen's theorem to this, so we could try writing this as a union of two circles joined at a point, and there's a slight problem here. These circles aren't actually open subsets. But that doesn't really matter, because I can change these two circles by adding a little open bit there and adding a little open bit there, and then you can see I can these are then two open subsets of this infinity symbol, so that's good enough. And these have the same fundamental group as a circle, because you can just push these little bits in. So the fundamental group of this infinity sign is just the free product of two copies of the group of integers, because that's the fundamental group of a circle, and this is just the free group on two generators. There's another way of doing this, the fundamental group of this. You remember we did the fundamental group of a circle by finding a sort of nice covering space. So you could sort of unwrap the circle and get a sort of covering space that looks like this, and then the fundamental group of the circle can be identified with the points lying above the base point of the circle. And you can do the same thing. You can try and unwrap this figure 8, and unwrapping it gets a little bit complicated, so I'm going to draw one of these circles in red and the other one in blue, so you can see what the difference is. And then if I unwrap the red one, I just get a copy of the real line with a lot of inverse images of the base point. And then I can also unwrap the blue circle, and I get another copy of the real line, so it looks like this. But then at this point here, I can also unwrap the blue circle, so I have another copy of the blue circle going through it like this, and I'm drawing it like this for a reason that will be obvious in a moment, because I can also unwrap the red circle here and here and here and so on, so I get more bits like this. But then through each of these points I can also unwrap the red circle, so I get more red things like this. And as you can see, it's getting what you notice is that I'm very rapidly running out of space. What I'm getting is this huge, complicated, infinite tree, and this tree reasonably obviously has trivial fundamental group, and it's also reasonably obviously a sort of covering space of this figure 8. In other words, for each point of this figure 8, its inverse image is a product of a discrete set in a neighbourhood. So the fundamental group of this figure 8 should be the identified with the inverse images of the base point in this huge tree. And if you sort of think about it a bit, you'll see that the inverse images of the base points can be identified with the free group on two generators. You see, I can write the two generators as A and B, and if I write B for this generator, you can see that any word in A and B and their inverses corresponds to a unique one of these vertices of this tree. Next example, let's try and do a torus minus a point. So what I'm going to do is I'm going to take a torus, and then I'm going to sort of poke a single hole in it. That's not a base point. I've actually sort of punctured the torus, and ask what the fundamental group of that is. Well, one very useful trick when you're trying to work out the fundamental group of a space is you should first simplify it a bit. And in this case, I'm going to do it by taking a deformation retractor, which means I try and squish this torus into something smaller. And it's easier to see this if I imagine a torus as being a square with the left side identified with the right side and the top side identified with the bottom. And now what I'm doing is I'm puncturing a point here, so I'm removing this point. And when I've removed this point, you see I can squish everything to the edge of this square by taking a deformation retraction. And this doesn't change the fundamental group, so the fundamental group is going to be the same as if I just take a square and identify the top and the bottom. And you can see that's the same as just taking two circles joined at a point. So the fundamental group of a torus minus a point is just a free group on two generators. So let's do another example to illustrate that. So a bit later I'm going to talk about the fundamental group of a knot, which actually means the fundamental group of a complement of a knot in three-dimensional space, which turns out to be a useful invariant. So several obvious knots: you might just have a circle, which is a rather trivial knot, or you might have a some sort of trefoil knot and ask what the fundamental group of the complement of that is. Well, that takes a little bit more effort. So today's lecture, I'm just going to ask what is the fundamental group of the complement of a circle in three-dimensional space. And there's one rather obvious thing you can do to get a non-trivial element of the fundamental group, which is just to have a loop that goes round like that. And there doesn't seem to be any other obvious way of getting an interesting element of the fundamental group apart from taking powers of this. And indeed the fundamental group is indeed the integers. And to see this, what we do is we first take a deformation retract of the exterior of the circle. In other words, you try and find something you can sort of squish the exterior into. And what you can do for this is you can sort of take a sphere around this circle. So I want to think of this blue thing as being a sphere, and you can push everything outside the circle, so everything outside the sphere onto the sphere. For everything inside the sphere, what I'm going to do is I'm going to take a diagonal of the sphere. And then if you think about it a bit, you can see you can push everything outside this circle but inside this sphere onto either this diagonal or the whole sphere itself. So the fundamental group is the same as the fundamental group of a sphere with a diagonal added to it. And you can simplify this a bit further, because if you've got a sphere with its diagonal, then what you can do is you can just move one end of the diagonal round until it joins the other end, and you can easily see that doesn't affect the fundamental group. So what we've got here is an S1 there and an S2 here, which sort of looks a bit like an S1 because I don't really know a good way of drawing an S2. And now what we've got is an S2 and an S1 joined at a single point, and as before, that's good enough to apply Van Kampen's theorem. So pi 1 of this is equal to pi 1 of S1 amalgamated with pi 1 of S2, and pi 1 of S2 is just trivial, and pi 1 of S2 is just z, so this verifies that the fundamental group of a circle really is just the integers. And in a later lecture we'll be working out the fundamental group of the complement of a knot, and we'll see that it's not the integers, which shows that the trefoil knot really is knotted. Another thing people very much like to calculate fundamental groups of is Lie groups. So we might have, say, the Lie group GL2 over the reals, which is just all 2 by 2 matrices A, B, C, D with determinant not equal to 0. So you can ask, what is the fundamental group of this space? And that's not easy to see immediately, because we're removing the things of determinant 0, which is a rather complicated looking set in 4-dimensional space, and it's a little hard to visualize. So we need to simplify this. And to simplify GL2, you remember the Gram-Schmidt process, which says that if you've got a pair of vectors, linearly independent vectors in 2-dimensional space, you can orthogonalize them. And if you think about what this is, it says that GL2 of R as a set is isomorphic to O2 of R, that's the orthogonal group, times the matrices with positive entries times the matrices that are triangular. So if you unravel the Gram-Schmidt process, you remember what you do is you first of all make the matrices orthogonal by adding a multiple of one to the other, which means you sort of multiply a pair of vectors by this matrix, and then you make them have norm 1, which means you multiply them by a diagonal matrix with positive entries, and what you're left with is a pair of unit vectors that are orthogonal, which sort of corresponds to an element of the orthogonal group. And the orthogonal group is just equal to a group of order 2 times the special orthogonal group. And the special orthogonal group is just a circle. And you notice this group here is pi 1 is trivial, and this group pi 1 is trivial, and this group here pi 1 is the integers. So we've worked out pi 1 of GL2 of R is just the integers. And we can do this in higher dimensions, so let's work out GL3 of the reals. Well, as before, we do the Gram-Schmidt process and we find this is isomorphic as a topological space to O3 of R times diagonal entries with positive coefficients times the things you need for making the vectors orthogonal, which is this set of matrices here. And this is just isomorphic to R3, which has fundamental group trivial, and this is isomorphic to a product of 3 copies of the positive reals, which is fundamental group trivial, and this is isomorphic to a group of order 2 times the special orthogonal group, over the reals. So we need to know what is the fundamental group of the special orthogonal group. Well, there's a neat way of doing this using quaternions. So you remember quaternions are the numbers of the form a plus bi plus cj plus dk. And if you look at the unit quaternions, these form a copy of the three-dimensional sphere. So this is the numbers with the set of quaternions such that a squared plus b squared plus c squared plus d squared equals 1. And the three-dimensional sphere has a map to the special orthogonal group because if you've got an element x in this three-dimensional sphere, it just takes an element v to x v x minus 1, where v is equal to a plus, where v is equal to something times I plus something times j plus something times k as a vector in R3. So S3 is trivial fundamental group, so that's quite promising. But SO3 doesn't have trivial fundamental group because this map is not an isomorphism. This map has a non-trivial kernel, and the kernel consists of the elements plus or minus 1. And what we have here is a covering space. So you remember I worked out the fundamental group of a circle by saying the real numbers were a covering space of it. So we have a, if we have a simply connected space that's a covering space of something, then the fundamental group of the something at the bottom is just can be identified with the inverse image of the base point. So exactly the same thing is happening here. So the kernel of this map is just the fundamental group of SO3. So we've worked out the fundamental group of 3 by 3 matrices over the reals. The fundamental group is just a group of order 2. It's actually obligatory at this point to demonstrate the soup plate trick. So the fact that the fundamental group of SO3 has order 2 can sometimes be understood by taking a soup plate and rotating it. Maybe if I just switch screens, it'll be easier to show this. So let me just get into a position where you can see this. So what I have is a plate, and you should imagine it's full of soup, so I can't turn it upside down, although it's actually not full of soup because I don't want to spill it. And what I'm going to do is I'm going to rotate it anti-clockwise 1 revolution, and you see my arm is really twisted. And if I rotate it anti-clockwise by a 2nd revolution, you might guess that my arm is going to sort of break off or something, but no, in fact I can do it like that. So you can check that this works. So what does this have to do with the fundamental group of SO3 being of order 2? Well, the position of the soup plate can be thought of as something like an element of the special orthogonal group, because I can rotate it by an element of the special orthogonal group. And my arm represents a sort of homotopy or a path from that element of the special orthogonal group to the identity element. And rotating it by 1 revolution kind of corresponds to having a non-trivial path from the identity rotation to the back to the identity rotation, because rotating by 360 degrees is the identity. And taking 2 copies of this path is actually trivial and means that my arm doesn't actually break off when doing this double rotation. Okay, so next lecture I'll be doing some more calculations of the fundamental group, probably trying to calculate the fundamental group of the complement of a knot. And if I have time, I might say something about the Alexander's horn 3 sphere.